So, thank you, Grace, for introduction. It's my great pleasure to make this presentation to discuss with my recent research. And today I would like to talk about the biomass-derived post carbon for the technical water treatment. And in my presentation, I would like to give you several of the cases which we use the different source of the carbon, different source of the biomass to derive those carbon and use those carbon as of those contaminants in the waters. So first I would like to give you a little bit of information about this water and water pollution actually is the big issue around the world. And for those of with the water treatment, we can have several different types of the technique. Often we use the chemical reduction, and also we can use the biochemical process, and also we can use all the contaminants in the waters. But for this water treatment, compared to the bio process and also the physical separation process, and more complicated to remove these contaminants much better than the physical process. And also for such a chemical process, the reaction rate generally is very fast, and oxidations need to have a very good oxidant to produce those of the reactive oxygen spaces so that it can help to remove all the contaminants. For the oxidants, typically we can have nitrogen oxide, some of the new oxidants. Often molecule in Genesis, we can have two different molecules. One is the peroxide non-sulfate, another one is sulfate. Advanced oxidation process, which is referred to the Fenton reactions. For the Fenton reaction, in the general way, we use the ions and also the nitrogen oxide. For the water treatment, because for this one, we have to take a very narrow pH range, and also for such reactions, it can produce large amount of the sludge from those reactions that results the ion which is used for the to overcome all these problems. So we can use the new type of ways of the oxidant, permanganate sulfate and also the persulfate. And for those of two different oxidants, we can see that for such as two different materials, we can generate sulfate radicals. And for those of the sulfate radicals, it has several of advantages than hydroxide radical. First, in an effective way, and also for such a persistent, we can take the running of a large range of pH. So in that case, it can be used for many different applications. But for those of these process in the general ways, we have to use some catalyst for those of the metal, if we reach into the water, it can cause the metal toxicities. So for overcome this sort of metal-based systems, carbons, because for those of the carbon, we have a large amount of available sources in the world, and also for those of carbons, they can be modified in terms of the structure and also in terms of functionalities. So basically, we use those of the carbon as the catalyst to replace these automated-based persistent, and we found that these are the non-metal-based persistent or carbon-based material can give us very good catalytic performance. But for those other catalytic performance, it shows some of the distance from this metal-based persistent based on our very large amount of the research. We found that for such a resistance, it can have radical reaction system, and it also has the non-reactive system. And for these are the two different systems, the carbons will play a very significant role in terms of the structure and also in terms of the functionality. We found that the load of the carbon is depend on the structure of the sp2 and also sp3, and it also depends on the nitrogen system. Also, the self-surface functionalities. So in that case, for all those different carbon systems, we need to have very good carbon structures, and also we should have very good doping systems into such a system so that we can optimize the carbon nanotube, or we can use the graphene as the catalyst. We can investigate its functionality. We can also use the structure to understand the reaction of it. But in the real applications, we cannot do this as nanotube. Cheap carbon sources, and then we can convert those of the cheap carbon precursors into a functionalized and also post the carbon. Tensions in terms of absorption and also in terms of catalysis. We know that the biomass actually is the large storage of those carbons, and for those of the different sources of those carbon precursors, we can take some of the very good chemical treatment or the functionalizations, and we can test the structure of the carbon and also functionalizations. So to check these sort of ideas and the basic incidents that we are trying to look at, if we can get those of the carbon from those biomass for the two functions. One is the post structure, and the other one is the functionalization, which is the nitrogen or the self-indulgence. So for this one, we tried the very basic structure of the biomass, which is on the glucose. So for the glucose, and we are trying to look at if we can use the very simple technique to produce both the functionalized carbon and the very good post carbon. So in that case, that we will a very simple technique for one port synthesis. We put some of the soybeans bionitrate, and also we put the nitrogen precursor or the sulfur precursor into such a systems under the high temperature processes. Precursor. One is for the nitrogen precursor, we use the urea, and also we can use nitrogen and sulfur precursor. So basically for these are two different precursors, and we produce nitrogen doped the carbon, and also we produce the nitrogen and sulfur co-doped with the carbon. But see from those and also ICM that the structures of this are full carbon. For the nitrogen doped carbon, we see clearly the layered structure, but for the nitrogen and sulfur co-doped carbon, we got the honeycombs of the structures. For these two different structures materials, we also can see that we have these two materials in the very high surface area and also across the structure. In that case, that these are two different of the materials can have a very good post structure for absorption, and also they have functionalized the group in in their structure so that we can also see for the nitrogen and sulfur, we have very good loading for the nitrogen and also for the sulfur. In terms of these of the distribution, we can also see that those of the nitrogen and sulfur are very well distributed in those of the carbon systems. And then we can look at these of the absorption capacity. First, we look at the carbon absorption and also the nitrogen absorption. And carbon dioxide absorption, and for the nitrogen absorption generally it is low, which means that for such a carbon materials, we can use the adsorbents to separate the carbon dioxide and also the nitrogens. But for the water treatment, we can also see in terms of the absorptions, both of the functionalized the carbons, they also give the very high absorption capacities, and these capacities are much better than the other. Also give the very good catalytic performance. And in another way, that we also try to look at those of the real biomass systems, because previously we only see the glucose. And when we look at the fluoride derived of the carbon material, we can see even we can take the same strategy to get the porous the carbon and also something like the carbons. Carbons, and also from those of the first structure that we can see that these are the materials with very good structure, and also the functionalization for the nitrogen distribution is also very good. And moreover, we can also look at the absorption in terms of carbon dioxide absorptions, and also we can see that for those of materials, they can also give us very good absorption of the CO2 absorption at 0 degree, 1 bar, and also 25 degree or the high pressures. They basically can give us very good absorption capacities. And also we try to look at with water treatment in terms of absorptions. We can also see that for use of the fluoride post carbon, we can also give us very good absorption capacity. And in terms of the catalytic reactions, they can also be a very good catalytic performance. So this is just to show that for all those of different carbons, they can give us the very good absorption and also the catalytic reactions. And for such as carbons, I already know that for the thinking reactions, it all depends on some of those metals. But in our case, we are trying to look at non-metal-based system, but we can still consider if we can combine the metal and this carbon together, so that we load the covalents into such a system, and we can get whole shards structures. So in that case, that we can see if this the kosher structure can still give the very good absorption and also the reactions. So from those of the results, I thought we can still see that in terms of the reactions of those metal loaded the carbon systems can give us very good activity, and it should much better the system. And also for such a way of the system, we can say that for the reactants mechanisms, it depends on both the radical system and also based on the non-radical systems. So in general way, we can see for the metal-loaded system, carbon systems, and the single oxidants and also the radical work for the degradation of those organic. So if we can introduce those metal inside a system, the metals can be the much higher of the non-radical base of the systems. And also, if we combine two of the systems, and non-metal will form a synergistic effect. of reactive species for the degradations. And later on, we are trying another systems and to use the real biomass because for previous two example, we use the glucose and also the flour, which is based on the plant disease. We just use the same technique to use the plant as precursor to get the system use the same technique, and also to get the very good carbon-based systems and build up the carbons. So the surface areas. And additionally, we also try to look at to dope some of those metals into such systems. And I've already found, you can see from these tables, in the general sense that if we dope the metal into the system, it can also get a very good surface area, even if it's a little lower than the non-metal-based system that is. And we can look at their performance for the degradation of those contaminants or in terms of absorptions. But for this case, we are looking at two component system. One is based on the phenol, and another those are the catalysts can still show some of the good catalytic performance. And we can see from these of the result, it generally tells us that for those of the two boundary of the systems, such a catalyst can still give a very good technical performance. Such a system for the degradation of those components, it depends on the pollutant structures. And for this case, we found that in terms of the phenol absorptions and also the HPA absorption, phenol absorption generally is not as good as the HPA, but in terms of the package, could be very strong reactions in chemical degradation, which is much better than the HPA. So in that case, we can see that for the same of those of the materials, those of the materials will show different chemical performance for those of two components. Radical spaces and also the radical spaces, they are playing different roles inside that systems. And what you can see from the results of magnesium investigation, we can see that for such a system is include both the radical and also the non-radical component of the different reactor spaces will play different roles in degradation of the two chemical components. And later on, we are trying to do more of the research to look at those of the other biomass. And in this case, that we use a natural product, which is yeast, because for those of the yeast, they actually have a large amount of the protein, which is referred to the nitrogens. Into such a system, we can use that increase the nitrogen components inside the system, and we can derive the nitrogen dose of the system. And for such a system, we try to make two different reactions. One is with the monosulfate and also the sulfate. And also we try to look at these of the catalysts for those of the two different component systems to look at their efficiency. And also we are trying to look at these of the catalysts in the PM activations for the degradation of the contaminant, we compare the single component system and the two component system. And from our result, we found that in general sense, for such other materials, they can still show the very good chemical performance in the single component. And also we can look at their two component system. And for some other systems, they also gave us two different type of the reactive spaces. One is the radical and the other one is the non-radicals. But for those are the two different systems, we found that in terms of the single component or in terms of the binary components, those are the candidates actually show a little bit of difference. I wouldn't believe that in terms of the two component systems, the candidates in a way will show the low catalytic activity. But in our case, we found that it is not just the component or the bar component. The bar component gives you the good catalytic performance than the single component. For the IGBA, gives you the stimulus catalytic performance. And we will also look at the single systems for the TS reactions, and we also look at these material for the PS degradation of those of the two components. We're doing the same way in the single component and also in the two components. And our results actually show that those of the material still show a very good technical performance, but in terms of the reactions mechanism, it still shows the two reaction mechanisms. One is the radical and the other is the non-radical system. But those are the two component systems, they show the different behaviors than the PMS system, because in the previous work, we found that in the single component or in the two component, for the phenols, the two components will show better performance. But for this other case, actually, we found that performance. But for another organic, we still show the similar technical performance, which contain one or two of those of the components. It really depends on the technical system and the radical and non-radical, which means that those of the radical and non-radical will play a different kinetic degradation of the results. Today we can see for all those of the materials, and we can use this of the carbon as the catalyst for the degradation of contaminant using TS and also TMS. But we generally found that for all those of the carbon, they actually show quite large of the activation activity in such systems. So to fully understand the activities, we also try to look at the material after degradation, and then we try to use the lower temperature calcination to regenerate this material. Can still be regenerated at the lower temperature after its calcination. It's also very show the very good regeneration ability to be reused again. Okay. And basically, I think that if we use some of those of the results which we derived from what we have learned, and in the general sense that we can see that for the different carbons, we can use those of the biomass as the resources for the carbons, and for those of different biomass, we can look at those of the different structure, and also we can look at the functionalizations. So in our case, we can use very simple technique to transform those of the different type of the biomass into a functionalized of the carbon, and for those of functionalized the carbons, they can get structure and also functionalizations. In these of functionalization of the carbon can be very good technical performance for the degradation of those different contaminants in the water. Okay, and I think we have stopped it, and thank you very much for your attention.